Hello and welcome to this series of linear algebra for machine learning. My goal is to just show not just show you the formulas, but to develop deep principle first intuition for mathematical structures that underline all of the modern machine learning. We will move from the basics and try to reach the level of some advanced research level applications. This is a foundational first lecture where we are going to build our entire from where we are going to start building our entire environment. Uh, let's get started. We'll learn the language of data, how we translate our complex high-dimensional world into precise structured objects a computer can reason about. We'll do this by touring real-world ML problems, and then we will dive deep and have a class on NumPy, the fundamental library for numerical computing in Python. A quick note on prerequisites though, a basic comfort with Python syntax like variables, lists, and functions is all you need. We will build all of the mathematics from the ground up right here. To follow along, the easiest way is to use the Google Colab link in the description. It's free, it's out there, and it requires zero setup. With that said, let's just begin the video. Uh, here we are in our Jupyter notebook, which we will serve as an interactive textbook for the series. Hopefully, in the first cell, I'm importing all of our core libraries, NumPy as NP, then which is like going to be the main character in today's video. And then we have pandas, you have got matplotlib and cbon. We'll explain this later. And cbon will help in reach some rich visualizations. So if we just run this, so with our environment ready, let's address the core idea of what we're going to do here. The entire field of machine learning, from the simplest linear regression to massive models like the GPT, is built on a single premise. We must find a useful numerical representation for our data. This process is called vectorization or feature extraction. uh, the output of this process, the vectors, the matrices, and the tensors that we create are the fundamental objects of study in linear algebra. So we'll go to this part one of why linear algebra, the language of data, where let's let's just do the four major domains that we have and see how we practice this representation. Okay, so first we have is a tabular data where I'm using pandas here. Here we have used pandas to create a familiar spreadsheet like structure for our house data. So this here right here, and each row is an observation. Is like an observation here. Each row would be an observation. Where like a single house, each column is a feature, like an attribute of that house. So how do we look at this? Like let's just execute this one here right here. And when we convert this NumPy object, when we convert this to a NumPy object, we get what you see in this heat map, a matrix. So formally, a matrix of r raised to m cross n, where m is the number of rows or samples and n is the number of columns. So now if we isolate a single row, like the data for house one, we get 15. We get this because this is we have isolated a single house as a vector. This is a vector. Specifically, it's a point in four-dimensional vector space R raised to 4, where each feature represents an axis in that space. The entire matrix is a collection of these vectors. Of the have here, which is image data. In image data, you can think of image as a spatial arrangement of pixels, right? So here I am loading a sample color image. Sample color image. Let's just first run this. So it will do this, and so it will load a sample color image. Its numpy shape is around this, which is 427, 640, 3. Uh, represent the spatial axis of its height and width. The third dimension of size 3 right here is the channel. Is the what's it called? The channel axis, which is representing the red, green, and blue. So this visualization makes it clear where the 3D tensor on the left can be decomposed into 2D separate 2D matrices, one for each color's intensity. If this were a grayscale image, it would simply be a single 2D matrix. This hierarchical structure, tensors composed of matrices, is a very fundamental concept that we're going to see here. And to do that, we have just visualized it right here and we've plotted it right here. Uh, So let's move on to the next thing that we have, and which is like generally quite famous, which is NLP. Being instruction and documents, a sentence can be a matrix where each row is a vector representing a single word. So let's get started with that. Uh, so text is perhaps, let's say, the most fascinating representation problem. How could you turn the word algebra into numbers? So modern NLP uses a technique called as word embeddings. We create a high dimensional vector space. Let's say r raised to, let's say just I'm typing here, r raised to, uh, r raised to 300. 300. Now this is something which is a high dimensional vector space where words with similar meanings are located close to each other. Here for the sentence linear algebra is fun, I am simulating this by creating a matrix where each row is a dense 8-dimensional vectors representing one word. Now here we have got here this. So I'll just execute here and just show it here. And yeah, so this heat map shows this sentence represented as a 4 by 8 matrix. The values within each vector are represented by neural network from analyzing billions of sentences. The geometry of the space these vectors live in captures the semantic of the language. This transformation of discrete symbols, the symbols being the words, into a continuous vector space is one of the uh, like great, good on the good discoveries of modern machine learning, let's say. So we have got another thing right here, which is the recommended systems, where user interactions with items like movie ratings or a large user item interaction matrix where rows are users and columns are movies. So the cells are ratings itself. So let's here we construct something what's called as a utility matrix. The rows represent users, as I said, the columns represent item, and the entries I comma j in bracket represent the rating a user I gives to the item j. So I'll just run it here, and as the matrix is typically enormous and sparse, meaning most of its entries are zero, as you can see from the dark purple square. Users have only rated a tiny fraction of the available items. The entire problem of collaborative filtering can be framed as a linear algebra problem. We want to find a low rank approximation of this matrix to predict the missing values, right? This is a topic we'll explore in depth when we cover, let's say, stuff like matrix factorizations like SVD. So, yeah. So, we have now established the why. Now, like why is this all required to some extent? This were just some examples. We'll go into depth later on. Uh, Now, for the how, like how do we do this? So we'll go use NumPy to construct and manipulate these objects. So the core data structure in NumPy is the ND array that we have, and or the n dimensional array that we, as it's called. It's powerful for two reasons. Its operations are implemented in low-level compiled languages like C, making them incredibly fast. And its data is stored in a contiguous block of memory, which is highly efficient. All right. So see, so it's just giving out for this. Computation that we're doing here. It's giving out the output here. So this is like we'll go through this first. So let's formalize our key terms and see how to inspect these objects. So now this is a simple 2 by 3 is it? Yeah, 2 by 3 matrix that we have here, and with the entire grid is our matrix, a single entry m, something like, just type for the sake of it, 0 comma 0. this whole thing this whole thing right here is is a scalar, right? So a single row, let's say this right here, is a vector. So let's look at the attributes. Dot shape that we have is a tuple that gives us the size of each dimension, 2 comma 3 that we have here. Dot ndim that we have gives the number of dimensions or the rank of tensor, which is 2 for a matrix. It's crucial to not confuse this with the rank of a matrix in linear algebra sense, which we will define later as the dimension of its column space. For now, think of ndim as the tensor rank, just to keep it crude. So yeah, so this is now array creation routines that we have. In practice, we rarely create arrays from lists. We use optimized creation routines that we have. We'll go into depth later, but let's just first execute that we have here. And so np dot zeros and np dot ones are used for initializations. Np dot arrange creates integer sequences. Np dot linspace is key for scientific applications. It creates a specified number of points with equal spacing, which is different from uh, arrange. What's it called? I'll just type it right here. Arrange this thing is fixed step size. So an np.random provides a suite of functions for creating arrays from various statistical distributions, which is fundamental for initializing the weights of neural network and for many simulation tasks that we have. So we have indexing and slicing right here that which is the most important skill that we have. It's one of the practical skill that generally people have as in a data scientist role, which is indexing. This is the syntax we use to query and select subsets of our data structures. Mastering this is generally non-negotiable in various places. Here I have a random 5 by 5 matrix, let's say, that we have. So if I just keep on executing this, it will give a random matrix, as you all can see right here. Execute it again, something else. So yeah, so the indexing is zero based, like in Python list. To select a single element that we have, we use the syntax m row comma column. So once that is done, so m0 comma 1 that we have right here, this that we have right here means select everything from this selects this element at the first row, second column. To select entire sections, we use slicing. The colon means select all elements along the axis. So let's say something like this that we have here means select everything from the second row. Conversely, let's say for this right here that we have means select everything from the third column. So we can combine these to select sub matrices, and you can do permutation combination with this a lot. Uh, this is the final example that we have right here, where we define a range for both the row and the column axes, giving us a 2 by 2 block in the top right of the original matrix. As you all can see right here, this is and this right here, the top right 2 by 2 subgrid that we have. Now we have gotten something that we need to see. But okay, so this is the reshaping and broadcasting methods that we have. And yeah, so these are some of the broadcasting visualization methods that we have. Just run it quickly, and yeah, so this is something you all can do as homework, or not homework, just just figure out it through uh, syntax. And yeah, so I leave this up to you all. And so yeah, so what we the next thing that we have here is the two core skills that we require for this lecture is like reshaping and broadcasting. So these are the operations that allow us to flexibly change the structure of our data fit into the requirement of our models. So we'll just run this right here. First, reshaping, we often reshape data in a flat 1D format, like a long list of pixel values. So machine learning models, however, usually expect, let's say, a multi-dimensional shape. So the dot reshape that we have, the dot reshape function, the dot reshape method is our tool for this. So we can create 1D vector with 12 elements. Its shape could be 12 comma blank, and then by reshaping it, I can restructure the same data without it getting copied into the memory. By the way, into a 4 by 3 matrix. So the only rule that we have here would be that the total number of elements must remain the same. 4 times 3 is 12, so this is a valid operation. So this is a constant task in data pre-processing people do, ensuring your data tensor has the exact shape of your model's input layer. the model's input layer, what is expecting, has the data tensor in the exact same shape. That is one of the constraints. So next, one of the most it's a good concept to have is broadcasting. Like let's say we want to add a vector to every single row of a matrix. The naive approach here would be to write a for loop iterating through the rows. This is slow in Python, so NumPy provides a much more efficient manner to do the same. Let's look at the visualization we have here. We have a 3 by 3 matrix, then we have a 1 by 3 matrix, and then when we write matrix plus vector, we are asking NumPy to perform an operation between arrays of different shapes. So broadcasting is the set of rules that NumPy follows to make this work. Conceptually, the NumPy stretches somewhat or duplicates the smaller array. In this case, our vector 10, 20, 30, so that it matches the shape of a larger array. So as you can see, it effectively creates a temporary matrix where each row is our vector, and then it performs the element-wise addition. The result is that the vector has been added to every row of the original matrix. This happens behind the scenes, implemented in highly optimized C code, and is the key for writing concise and fast numerical code that we have. So yeah, that was that. Let's move on to some of the few exercises that I have been provided here. So you all can go through this while I'll go through the solutions for now. Uh, so first, a simple warm-up could be, create a 1D NumPy array containing the numbers from 10 to 50 with a step of 5. So here we have got exercises for the same. So if we just run this, it will do the same uh, containing. So this is a perfect use case for np dot range that we have. So we could do the same. So this is so the start is 10, the stop is 51 because it's exclusive, and the step is 5. So then and here we have it, the output that we have. Now take the array from the previous exercise, and it has 9 elements, right? 1, 2, 3, yeah, 9 elements. So reshape it into a 3 by 3 matrix. So if we just run this again, so this will do the same. And there we have a 3 by 3 matrix. So then we can create a random 5 by 4 matrix. Okay, run this again, it will create a random one all the time. 5 by 4 matrix representing a data set of 5 students and 4 exam scores, let's say. So the score should be between the integers 5 and 100, and hence we have 101 because it is excluded value here, is exclusive value, and the size is 5 by 4. So from the student matrix, we just select the scores of the third student, which is at index 2 by the way, and then select the scores of all the students for the fourth exam, which is at index 3. So if we run this, so it will obviously give this answer. We can see right here. So yeah, so and about Boolean indexing for find all the scores that are considered A grade, that is like greater than or above 90. So greater than or equal to 90. So if I run this again, so now we have all these values because we have changed the matrix again as it was a random matrix that was selected. Uh, Now we have got a broadcasting challenge as of sorts. Where you have the 5 by 4 matrix, curve the grades by adding the following points for the 4 exams. So this will require broadcasting one D vector into a 2D matrix that we have. So this is, you can put in all your solutions here, but this is how we do it generally. So if I do this, yeah. So here we have the output right here. Leave it to you all to interpret it. What another exercise that can be done, which is not uh, beginner friendly but can be done, is like create a random 3D tensor of shape, this representing a small color image. Use slicing to set the green channel on the top left for 10 by 10 pixels to pure green, like value 1.0. Visualize the image before and after the modification. So this we have done here, the values are between 0 and 1, so it will be of different values, and then modified image would be having these values red, green, and blue. And then we plot it again, and this is the visualization part. So then as you can see, from 10 to 10 it has become purely green. And yeah, this is our first lecture, just basics of what we could do. We'll be diving deep into linear algebra. This is just like a basic introduction lecture that we had today, like representing data and all of that. So if I just run this again, so this is like creating, this is some of the other exercises that we have. So yeah, So like creating synthetic data, user data, and then matrix slicing that we have, Boolean index. So all of this would be available in the GitHub repository in the description. And what does the original matrix mean? Or does the normalized matrix mean? All of these would be available in the GitHub repo. And just just go through the tensor operations part as well that we have here.